On our next example, we're going to take a look at example 1, where a car is traveling north at 48 kilometers per hour. So let's sketch that car. So let's say this is the car, sorry for my non-artistic abilities here. It's traveling north in this direction and traveling so at 48 kilometers per hour and is approaching an intersection. A truck traveling east at 60 kilometers per hour is moving away from the same intersection. So moving away means that it is currently at the intersection right here and moving in that rightwards direction. So we will draw an arrow indicating it's driving in that direction. And then the question is, how is the distance between the car and the truck? And here is our truck. How is the distance between the car and the truck changing when the car is 9 kilometers from the intersection and the truck is 40 kilometers from the intersection? So when we are looking at the distance between the car and the truck, that would be this segment here. So we can see we're going to flesh out a right triangle when we connect that. And so I like to use the variables associated with the direction. So when we are looking at a vertical distance, we'll call this y. We'll call our left-right truck motion x, and the distance between them z. So it will lead you guys to think about Pythagorean theorem. Okay, so anytime we have something triangular, that's going to be the first thing we think of on the relate part. So right now we'll list out what we know. And what we know is that the car is traveling north at 48 kilometers per hour. So since that's a rate and the variable associated with the distance between the car and the intersection is y, we'll write that as a rate of change. So the derivative of y with respect to time is given to us as 48 kilometers per hour. A truck traveling east, so the truck is traveling away, so his distance is growing. And keep in mind, when I did the car was headed towards the intersection, so this distance right here actually is shrinking. So we're going to go ahead and use a negative value for the rate of change for y, because again, this distance is shrinking as the car moves closer and closer to the intersection. So with that, we're going to make our rate negative, whereas with the rate of change for dx dt, we're going to make that positive because the distance between the truck and the intersection is growing. So negative 48 and positive 60. How is the distance between the cars? So the question is what we want. How is the distance between the car and the rate changing when the car is 9 kilometers from the intersection and the car again is y, and when the truck is 40 kilometers, which is x? So what we want is the distance changing, rate of change. So dz dt, this bar is to indicate certain moments in time quantity values. So for example, at the moment, we want the rate of change at the moment the car is 9 kilometers from the intersection. So for me, I draw that bar and I write when y is equal to 9 and when x is equal to 40. Okay, how all of this is related. So how is the variable x, y, and z related? Simple, it's related by x squared, y squared equals z squared. That's Pythagorean theorem. And then we're going to go further in describing this as when we're looking at this, is x changing, y changing, z changing, or is anything fixed? So if I look back at the picture and I see if the car is approaching the intersection, y is changing. If the truck is moving away from the intersection, x is changing. And while both of these, while both of the vehicles are moving, z is also changing. So we can't fix any value to it. So two things usually occur. What we're going to identify, like the ladder problem, anything if it's fixed. Since nothing is fixed, we can't do anything from that. We do want dz dt, and we're given dx dt and dy dt. Also notice that when they ask for dz dt, they want it at a moment in time. So there's two things that we can do with this relate equation. So before I take the derivative, I'm also going to think of x squared plus y squared equals z squared at a specific moment in time. Eventually, I'm going to need the value of z, and right now, since we are going to find the derivative of z with respect to time, we already are given y is equal to 9 and x is equal to 40 at that moment in time. So we can solve for what z is using Pythagorean theorem. So I'm going to plug in x as 40 squared plus y, which is 9 squared. And at the moment when x is 40, y is 9, and if I solve for this, I'm going to get z at that moment is 41. And so now I go back to my equation, and so that's one thing I'm going to do with the equation. The other thing I'm going to do is now continue with the relationship by taking the derivative with respect to time. So we have 2x times dx dt plus 2y times dy dt. And this time, unlike the latter problem, z is also changing. So 2 times z dz dt. Notice that we have 3 terms here, one here, one here, and one here. They all have a 2 in it. So we're going to divide everything through by 2. And we have 6 variables here. X times dx dt, y times dy dt, and z times dz dt. And we're going to substitute in all the values we know. We have y, x, z, and we also have dy dt and dx dt, which then leaves us with what we're wanting to find, which is dz dt. So let's go ahead and substitute all the constant values in. I'll do that right underneath that, and then we'll solve for dz dt. So we have x is 40, we have dx dt is 60, we have y is 9, and we have dy dt is negative 48, z is 41, and then we're solving for the variable dz dt. And so if I solve for dz dt and isolate dz dt, I get 48 kilometers per hour.